That's a bit late. You should say that earlier. Okay. All right. So it's good to be here in the room, I think. I've just been talking about why we actually need to distinguish between these two kinds of validity about the relevance and the exogeneity. All right. So what happens if any of these conditions is violated? That's the first question we need to think about. Do we still get valid statistical inference? And then also we need to answer the question, how can we detect if there's a problem? Because we need some formal way, or hopefully some formal way to find out whether there is a problem or not. And if there's a problem, how can we heal that? Is there any way to find a remedy to get a better estimation, to avoid those problems? So these are the three guiding questions that we should think about. So let's start with the relevance. And the question, if the instruments are relevant, is difficult to answer if we have many endogenous regressors. But in most applications, in most economic applications where instrumental variable estimation is used, there's only one endogenous regressor. So that's a simplification that is perfectly plausible in a bachelor course. So we assume for the moment that we have only one endogenous regressor X. But of course, we might have many exogenous variables. And as you might remember, we had a different notation for the endogenous and the exogenous regressors. The endogenous regressor, well, it's only a single one here, is denoted by X, and the exogenous regressors are denoted by Ws. Okay. And then, of course, we have the instruments X1, Z1 up to Zm. So we assume that we have more, or potentially more than one instrument, even though we only have one endogenous regressor. So we assume that at least we have exact identification. Identification means we have, in this setting, means that we have at least as many instruments as we have endogenous regressors. Okay? So if there's only one regressor, we need at least one instrument, of course. We could have more, that's better, but we need at least one. Okay, then to find out whether the instruments are really relevant, we might run a first stage regression. And remember, the first stage regression is a regression model which we are not really interested in. The first stage regression is running a regression of the problematic regressor, the endogenous regressor, on the exogenous instruments and on the exogenous variables and the instruments. So in this case, we run a regression which we are not really interested in. I mean, after all, we want to know the effect of X on Y, the causal effect of X on Y. But here we run instead a regression of X on the instruments and the exogenous variables. So this first stage regression answers the question, can we, using the instruments and the exogenous variables, can we somehow predict the good component of our problematic regressor? And the instruments are relevant if we can. So let's look at the regression equation. We have a number of parameters here. We have the intercept, that's just a nuisance parameter in a way. And then we have the slope coefficients for the instruments and the slope coefficients for the exogenous variables. Well, of course, the exogenous variables should have some impact on the X. No, they need not, but they could have some impact on the X. But what we really need is an impact of the instruments on X. Because we want to know what is the good component of the X, of X. Okay? So what we actually want to have is predictive power of the instruments concerning the endogenous regressor X. But that's a question that we already can answer. Because what we actually are asking here is, can we, using the Z values, predict X better than using only the W's. Now that's not correctly formulated. So using all the instruments and all the exogenous variables, do we have a better prediction of the X's than in the case where we only use the exogenous variables? So do we have additional predictive power of the instruments? That's what we need. And since the instruments are exogenous, this predictive power will split the X's into its two components, the X into its two components. All right. If there are any questions, just ask. Okay, how can we do that? Well, that's pretty simple, because there is predictive power of the instruments if these slope parameters are not zero. When they are zero, then there's no predictive power. So if not all of them are zero, then we have predictive power. So let's test whether we have predictive power concerning the set of instruments. Let's test whether pi1 is 0 and pi2 is 0 and pi m is 0. So we are going to test whether these coefficients are all equal to 0. There are m coefficients, so we have m restrictions, and that's the classical F-test. You've done that before. Yeah? So there's actually nothing really new here. We can run an F-test on the first stage regression to determine whether the instruments have predictive power on X. That's, in a way, that's quite simple. All right, if all these slope coefficients are close to 0, then we would have no or just little explanatory power for the X's. So let's ask, what are the consequences? Suppose all these coefficients are actually 0. And we derived actually this formula in an even further simplified setting, where we only have one endogenous variable and only one instrument. So in this setting, that's where we started when we talked about instruments. In this setting, we can derive the two-stage least squares estimator, which is in that case just the fraction or the quotient of the covariance between y and z. So the endogenous variable and the instruments divided by the covariance of x and z. So the endogenous regressor and the instruments. Now what happens if there's no predictive power? No predictive power simply means that there's no covariance between the x's and the instruments. So in that case, the covariance between x and z is 0. And the estimated covariance between x and z is probably not exactly 0, because there's always some kind of noise. So even if the theoretical covariance is exactly 0, the estimated covariance will be just close to 0. But that's bad enough. If this is very close to 0, then what you get here is something which is really very, very noisy. Because if the denominator here is very close to 0, the whole thing just explodes. Yeah? And you will get a beta 1 hat value, an estimator for the slope coefficient you're really interested in, which will vary really widely from almost minus infinity to plus infinity. So anything could happen here. And the estimation is essentially worthless. Okay. So if the covariance is, if the theoretical covariance is 0 or very close to 0, then the denominator down here will let the whole thing just explode, and you will get really large changes in the estimator. So just by chance, you might get a very, very low value, negative value, or just by chance, you will get a very, very high value. Yeah? And each sample that you draw in your head, so that's just a thought experiment, but each sample that you draw would give widely different results. So in other words, if you know this problem, then you can't put any trust in the estimated values that you get. So that's a severe problem. All right, so small changes in the covariance cause large changes in the estimator. Also, the estimator is no longer normally distributed. Remember from last week that usually the two-stage least squares estimators, they are normally distributed, which means that we get the variance of the standard error, and we can very simply construct a confidence interval. The confidence interval is just point estimate plus minus roughly 2 times the standard error. And if you want to perform a test, you take the estimate, you subtract the hypothetical value, and you divide by the standard error. And again, you use the critical values plus and minus 1.96. That's very easy, that's just standard. But if the instruments are weak, then this won't work. So the estimator is no longer asymptotically normally distributed. So in other words, the confidence intervals that you construct are wrong. And wrong means, yeah, what does wrong mean?
We can't be sure anymore that the error of first kind occurs with a certain percentage.
Exactly. So usually you construct a confidence interval in such a way that it covers the true value with 95% probability. And here, this won't happen. So it might cover the correct value or not, but a priori, the probability that it does is not 95%. So it could be much smaller. And then you have a problem because you think that you get the true value, but you don't. So you base your policy on some estimated causal effect, but in reality it doesn't exist, or it's of a different magnitude. And of course that's a problem. That's really a severe problem. So that the estimator is no longer normal is not just a technical nicety, or non-nicety in this case, it's really a problem. Okay, so the statistical inference is no longer valid, and one might think that's a suggestion of the authors of the textbook. One might think of weak instruments as, in a way, decreasing the effective sample size. So, in reality, your sample size might be 2,000, but since the instruments are weak, it appears as if the sample size is only 50. And since you do not really realize this, you have a problem because you think that you found something, but you haven't. All right. So how can we test if the instruments are weak? Well, let's go back to the slightly more general case where we have many instruments, but only one X. And I've just talked about that. So if the instruments are relevant, then not all these coefficients must be 0. Some might be 0, but not all of them must be 0. Okay, so in other words, we do have weak instruments or irrelevant instruments if they are all 0. So that's the case that we need to rule out. And therefore, we run the first stage regression. We regress the endogenous regressor on the instruments and the exogenous variables. And we check using an F-test whether all instruments have 0 predictive power. And that's a standard F-test in a way. And we can see whether the instruments have predictive power, joint predictive power or not. It's a joint test, just as the normal F-test. And actually, this is just outputted by any statistical software. Okay? So the F statistic for this is just reported in a standard way. So in a way, that's pretty easy. And we can use the value of the F statistic as a measure of the instrument's strength. But what we cannot do, and it leads a bit too far to really go into the details here, what we cannot do is to use the standard statistical inference that you have learned to really ensure that the instruments are relevant. So we need an F statistic which is much larger than usual to say that the instruments have enough predictive power to be useful in this two-stage least square regression. And which value of the F statistic is really large enough? That's a bit a matter of taste, but Stock and Watson argue in a, I think, reasonable way that a good rule of thumb is that the F statistic must not be smaller than 10. Okay. So we do not use the usual statistical inference and look at the p-value of this joint test. We use the F statistic itself and check whether it's smaller or larger than 10. And if it's smaller than 10, then you should be really careful and probably not use these instruments for two-stage least square regression. So it's not sufficient to test the joint significance of the instruments in the first stage regression. Formally, this is what we do, but we need a stronger criterion than the usual significance because we want to go further. We want to use the results of this regression as input for the next regression. And therefore, we must be, in a way, more sure that the results are reliable. That's the reason why. Okay. So the explanatory power of the instruments must be large enough. And there's a very easy rule of thumb. What we mean by large enough, we mean that the F statistic is larger than 10. That's, in a way, that's easy to calculate. It's just spit out by any computer package. So that's the relevance. And what do we do if we find out that the instruments are weak? Well, the trivial advice is, well, go out and find better instruments. That's trivial. Of course, it's true. And that's, of course, the best way. You need to find stronger instruments. You need to find variables that can explain the endogenous regressor, that can explain the X, that are connected to the X, but that do not have a direct impact on the Y. But as I just said, you have to learn to think up stories why you have connections in all different directions. So you will find a story why your instrument is connected in some way to Y. So it's really hard to find instruments that do have an impact on X, but not on Y. Not directly on Y. Only indirectly via the X, of course. Okay, so yeah, find stronger instruments. That's the best way, of course, but it's hardly doable in many cases. Then another advice could be to drop the weakest instruments. If you have quite a large number of instruments, that might work because then the F statistic might increase. The F statistic also takes into account the number of instruments, but the standard errors can nevertheless increase because the predictive power will still not be large, of course, if you drop the weakest instruments. All right, and then finally, there are also more modern estimation methods. I mean, after all, this two-stage least square regression is from 1928, I think. There are more modern approaches, but they are really very advanced. And in today's empirical economics literature, you will find the classical two-stage least squares estimation a lot. So that's still the standard economic approach to dealing with endogeneity problems. Okay, so we won't talk about those more advanced approaches. Okay, that's the relevance. So we need two properties, relevance and exogeneity. So let's talk about exogeneity next, or are there any questions?
So if we drop the weakest instruments, does that mean that we sacrifice the DSLS standard errors to be bigger? And so we sacrifice a bit of precision in that area. And in return, we get a bigger F statistic, which means that we can be more sure about the data that we get out of the the
first stage.
Yeah.
Exactly. Yes, absolutely. Okay. So exogeneity. What does exogeneity mean? Once more, it means that the instruments are not correlated with the error terms. And it really means that all instruments are uncorrelated with the error terms. So all these covariances must be equal to 0. And if that's not the case, so if any of these instruments is actually not exogenous, then the first stage regression has a problem. Let's go. Do we have the first stage regression here? No, but we have one here. So what happens if the instruments are not exogenous? That's the first stage regression. Well, if they are not exogenous, then any of these instruments is correlated with the error term. And that means that we have an endogeneity problem in the first stage. So in that case, the instruments, of course, won't work. So in that case, the decomposition of the X into the good and the evil component won't work, or at least it won't work correctly. And therefore, the estimation gets inconsistent in that case. Okay, how can we check? So that's the problem. We get inconsistent estimators. How can we find out if we actually suffer from this problem? Well, testing exogeneity is possible under certain circumstances, but it's not possible if we are in a situation of exact identification. Exact identification, just to remind you, means that we have as many instruments as we have endogenous regressors. So usually one each. We have one problematic regressor, 1x, and we have one instrument to remedy this problem. That's the situation. And then if we only have one instrument, then we just can't check the exogeneity of the instrument. In particular, one idea might be to check whether the empirical covariance between the instruments and the residuals is non-zero. So the theoretical covariance is the covariance between the instruments and the error terms. We can't see the error terms. We can see the instruments, but we cannot see the error terms. But we have a way to estimate the error terms. So it might be a good idea to check whether the instruments are correlated with the residuals, which are estimates of the error terms. That's a pretty nice idea. The only problem is that we use the uncorrelatedness of the error term and the instruments to do the estimation. So empirically, the covariance between the instruments and the residuals is always exactly 0. That's just our input into the estimation. That's our assumption, and we use this assumption to get the estimation. And of course, if we use this assumption to get the estimation, it's satisfied. So that's no way to check the exogeneity problem, even though it's a good idea, but it doesn't work. So that's not possible. The only way to check exogeneity is to use over-identification. So if we have more instruments than we actually need, at the minimum, then we can estimate or we can check the exogeneity property. So that's the only way. Oops. And that's called the J-test. And it's a kind of advanced test, but since it's reported by most software packages, let's talk about that. Let's look again at a simplified situation where we have one endogenous regressor, only one, but two instruments. So that's a situation where we have over-identification. If we have two valid instruments, that means that we could use the first instrument to do the two-stage least square regression, or we can use the second instrument to do the two-stage least square regression. So we have two different ways to do the same estimation. And the idea of the J-test is related to the idea that we actually do run these two regressions and check whether they are very different from each other. They shouldn't be very different if the instruments are correct, if they are valid, because in that case, everything goes smoothly. So if both instruments are valid, then using the first instrument, of course, gives different estimates from the second regression where we use the other instrument, but they shouldn't differ too much. That's the idea, the testing idea. So we run two regressions, we look at the results, and we say, well, this is different, of course, but not much. That's different, but not much, and so on. So if they are reasonably close to each other, then we say, well, both instruments are probably valid. But if we find that in the first regression, we get totally different results from the second regression, then that's an indicator that one of the instruments is wrong, is not valid. That's the idea. The problem is we don't know which one. Yeah? So in a way, it is a test of exogeneity, but it's not really constructive. It doesn't tell us kick out the first instrument or kick out the second instrument. It only tells us, well, one of these two is probably correlated with the error term. We don't know which one, but you shouldn't use both of them in your regression. So that's the idea of the J-test. So we, this is of course implemented in a slightly different way, but that's the intuitive idea of the J-test. Right, that's the formal implementation of this approach. And if the p-value of the J-test is very small, you tend to look at the p-values. And if the p-value of the J-test is very small, then something is wrong. That's all we can say. Something's wrong in that case. We don't know what, but at least you shouldn't trust that regression estimation. Okay, any questions concerning the exogeneity? This course here is about methodology, so we don't really do the empirical work here. We talk about how to do empirical work in general. So what's the methodology? So it's easy to say that you need more instruments and you need valid instruments, but of course, in real applications, finding instruments is really hard because there's always some kind of impact that you could think about. So valid instruments must be relevant and exogenous. So they must have predictive power for the X, but they must not have a direct impact on the Y. And that's usually really a problem. So being economists, I mean, after all, you're not statisticians, you're economists, and you're interested in economic theory and validating economic theory from data. So the first approach is, of course, to use economic theory. And sometimes that actually works. So sometimes you could use economic theory to say that certain variables should be exogenous. For instance, prediction errors should be uncorrelated with past data. That's an approach, because if you could use the past data to get, if the past data are correlated with the prediction error, then it would be very easy to improve the prediction looking at the past data. Okay? Everybody would do that. So you already have implemented the predictive power of the past data in your prediction, and therefore there's no more predictive power of past data. Okay? So prediction errors should be uncorrelated with past data. Prediction errors, that's the important part here. Of course, the predictions are correlated with the past data, but the prediction error should not be. Okay? Just think about predicting the value of the DAX index next month. Of course, you will make a prediction error, but if you find out that looking at many months over the years, that the prediction error is always too small, then something is fishy and you should improve your prediction. So that's the idea why prediction errors using economic theory must be uncorrelated with past data. So that's one approach. Quite often it's a good idea to use past observations as instruments. But in this course, we've up to now always talked about cross-sectional data. So there are no past data. We only have cross-sectional data. Yeah? And therefore, this advice is, well, kind of not really good. The second approach is to find variables that really cause exogenous variation in the X. So use variables which are just outside the economic system. Weather. Yeah? So that's like in the butter example we talked about first. If there's more rain, there's more grass, the cows give more milk, and there's a higher supply of butter. So rain has an impact on the supply of butter. That's how we can separate these effects. And of course, the rain won't be correlated with the price of butter. And just because butter gets more expensive, it doesn't rain more or less. So weather might be a good variable because it's truly exogenous, at least in the short run. And if you look at climate change, then things get more difficult, of course. But in the short run, the weather doesn't respond to any economic variable. Okay. Also, any other kind of natural, well, usually natural disasters. So earthquakes, they are quite exogenous. You don't know when they are going to happen. And if they happen, they just occur somewhere. So that's really exogenous. And it's not correlated with economic variables in those areas. Yeah, but that's about it. So there are not that many really relevant exogenous variables. So it's really hard. And so the take-home message here is finding valid instruments. That's easy to say, you should find valid instruments, but it's really hard to find them. Okay. Oh, there's one famous example. That's the, I don't know if you've done that in the exercises maybe, that's by Krüger, a nice paper, pretty old. And they looked at the sex of the first two children in a couple has. So if the first two children have the same sex, then the couple has a much higher probability to have a third child than if they are not same sex. So if you have two boys, you're more likely to have a third child than, or two girls, than if you have a boy and a girl. So apparently many couples prefer to have children from both sexes. Okay? Actually, I have 3 children, 2 boys and then a girl. So that's really a good example. That's exogenous variation because whether you get a boy or a girl is just random. And therefore seeing, looking at the first 2 children is a good example to find a variable that has an impact, but which is truly exogenous. All right, so that's the exogeneity problem. Any questions? So instrumental variables are really relevant if you are interested in causal effects. So that's one of the 2 main techniques that's still used today in the empirical literature. And you, as economists, you really have to know this methodology, and you really have to be able to apply that. You have to be able to understand what other people are doing. You have to see the limitations of this methodology, and you have to be able to do it yourself. Okay, so as I just said, that's one of the truly important methods that are used to tackle the endogeneity problem. So there must be more than this one. And the second one is using panel data. And this will be then the final topic of this course. So if there are no more questions concerning the instruments, then we will continue here with panel data. Okay, so what do we mean by panel data? We talked about that in the very first week, but let's repeat that. Panel data are data where we observe the same individuals of the same entities for more than one period. So in a way, it's a kind of repeated cross-section. But the second cross-section consists of the same individuals as the first one, or at least there must be a high overlap. Okay? So we look at many individuals in many time periods, or many firms in many time periods, many whatever in many time periods, at least 2 time periods. So the shortest panel is only 2 time periods long, and it's hardly worth being called a panel, but it's called a panel. Okay. All right, so let's ignore the problem of the endogeneity issue, and let's go back to the just simple multivariate regression model, where we have k regressors, x1 up to xk, and 1 endogenous variable, y. Right, so now we have many individuals and many time periods, and therefore we need a way to write that down in general. And the notation that's usually used is this one here. So we write x with 3 subindices. The first one is the number of the regressor. So x1 is the first one, x2 is the second one, and so on. And then we have 2 indices for first the individual and second the time period. So it's x1it. And whether you use a comma here or not, that's really a matter of taste. So x1t means the value of the first regressor for individual I in period t. And so on for the other regressors, and also for the endogenous variable. So this is the value of the endogenous variable for individual I in period t. We assume that we have little n individuals and capital T periods. So n is usually large, and t is, depending on what kind of data you have, but most of the time not large. 10, 5, but it must be at least 2. All right, there are 2 kinds of panels. The first one is called a balanced panel. Das heißt auch auf Deutsch so, ein balanciertes Panel. And that means that we have observations on all individuals in all periods. And if the panel is not balanced, then it's unbalanced, unbalanciert, which means that for some individuals, we do not have all the data. This can happen because an individual just moves away or dies, or it's not relevant anymore. So if you have a panel of workers, then individuals who retire just drop out. So you might have 2,000 workers you look at in 1 year, the next year, and the third year, but out of these 2,000 workers, only 1,900 remain in the second wave, and maybe 1,500 remain in the third wave. Then it's an unbalanced panel. That's more difficult because it depends why people leave the panel. So there might be different reasons, and this might be necessary to take that into account. So we will focus on the first case, the balanced panel. That's a little bit easier. All right, so this is how panel data might look like. So we have first the entity. So in this case, it's not individuals, but states, US states. So Alabama is the first one, then Arizona is the next one, and the last one is Wyoming. And that's the I, so the entity, the I dimension. And here we have the T dimension, the time. So in Alabama, in 1982, we observed these two values. In the same identity in the next year, we observed these two values. And in 1988, we observed these two values. This is all for Alabama. Then these dots apparently are wrong. So the next state is Arizona. We start again in 1982, 1983, and so on. And in the end, we have Wyoming in 1988. Okay. So this is a way to write down panel data. And that's the good way, the pure or the tidy way to write down panel data. That's the way you should strive to use. Here we have two variables, Y and X. We have the traffic fatality. This is the number of dead individuals, of people who died in that year by a traffic accident per something. I think the number of dead per 10,000 inhabitants or something. Okay. So out of 10,000 individuals, about 2 die every year in Alabama. About 3 die every year in Wyoming. That's one variable, the traffic fatality rate, and the other variable is the beer tax. So here you have a beer tax of 1.54, and so on. In Wyoming, the beer tax is much lower, it's only 0.04. So there's a lot of variation in the rate. Okay, let's have a look at those data, because we want to know, for policy reasons, what is the causal effect of the beer tax on the traffic fatality rate. If we want to drive down the number of traffic accidents or traffic deaths, then one way might be to increase the beer tax because people drink less. We've seen that addiction is much less important than one might think, so that might work. People drink less, so driving gets more safe, and we have fewer fatal traffic accidents. So that would be the causal effect. And we are interested in, does it really exist? And how large is it? And one way to start with the analysis is just to ignore the panel approach and use data from 1 year, in which case we have a cross-section of data. So let's use the first cross-section, that's the data from 1982, and just ignore everything else. So it's just a normal regression, just what we did all the time. So you run the fatality rate, you run a regression of the fatality rate on the beer tax, and this is what you get. This is the intercept, 2, and this is the slope coefficient. It's not significant here, as you can see, but if you do the same for 1988, it is significant. So it's positive, which means that we increase the beer tax and we have more people dying in the traffic. That's weird. And I haven't repeated this for all the years, but I guess it's relatively stable. So if you rerun this for 1983 and 1984 and so on, you will probably get similar results. There's some kind of variation here, as you can see, but I guess most of the time this coefficient will be positive. This is not really intuitive, and this is not what one would expect. And if the results are really counterintuitive, then most of the time something is wrong. So what might be wrong here?
Maybe the government always rises the clear text and the fertility rate rises as well. So because of that, clear text has a positive effect on the fertility rate because the behavior of the one who makes the text is wrong in some kind of way.
Yeah, so let's just briefly repeat that. So the argument is that we have a case of reverse causality. So it's not the beer text that drives the fertility rate, or at least not only, but also the fertility rate will have an impact on the beer text, because politicians that are faced with very high fertility rates are more likely to increase the beer tax. So the beer tax will be high in places where the fertility rate is high, which is just what we find here. So if you reverse the causal direction, as you should just exercise all the time, then this result becomes more intuitive. Other reasons might be, for instance, omitted variables. So this is the same again as a scatter plot or two scatter plots. So we can see that the OLS estimate is, well, not significant for 1982, but it is significant for 1988. And what we see is the higher the beer tax, the more traffic fatalities we have, which is strange. So it might be an indicator of omitted variable bias. So the quality of the cars might be different in different states. The quality of the streets might be different in different states. So in poor countries, people might drink more and they have less safe streets than urban against rural behavior might be the difference between these states, and so on. So cultural acceptance of drinking and driving might also be wrong. So it might be just common practice in some US states to drive even if you're drunk. I don't know. But in that case, those places are more likely to have lower beer taxes than other places. Okay? So we have different reasons why we could observe this strange result: omitted variables, reverse causality, and so on. Okay. So let's concentrate on this idea of, cultural acceptance of driving and drinking. If it's accepted in certain states that you drive even though you're drunk, then those places probably have lower beer taxes. I think plausible. Okay, so this variable might be an omitted variable which causes form of bias. And if we have this kind of omitted variable bias, then we should try to find we should try to include the omitted variable. So we should try to include the cultural attitude into our regression model. But how could we do that? Yeah. Yes, you could ask the people, what's your cultural attitude? But it's really hard to measure, I think. At least it's probably much harder to measure than, say, just the traffic accidents or the beer tax. In any case, on what scale are you going to measure the cultural attitudes? Is it just nominal? So yes and no, or more on a scale from 1 to 10? Yeah. Okay, so if you use the scale from 1 to 10, or 0 to 10, which is quite often used, you have the problem that it's not a metric variable. So even though you have numbers 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 8 doesn't mean that you're twice as well severe as if the value is 4. So it's really hard to, well, you have an ordinal scale in that case. And the regression techniques that we use don't really work if you have ordinal data. There are regression techniques, of course, which take that into account. But here, measuring the cultural attitude is at least more problematic than the other variables.
We would start by focusing on only one state, and then compare the penalty rate with the fixed rate. So we have this calculus aspect. So by only looking at state, I think it's quite plausible to think that, for example, people in Wyoming are kind of say cultural attitude.
So the idea is that the cultural attitude is fixed in one state. It doesn't vary over a couple of years. It might vary over decades, but not from 1982 to 1988. And then just look at the time series data in one state. And in that way, to hold fixed the cultural attitudes. So there are two approaches. The first one is get the data that might be omitted here and improve your regression. Of course, that's the golden way. And the second approach is to somehow hold fixed those variables that might vary, but where you could reasonably assume that they do not vary much if you focus on one state. All right, and this is what we are going to do. So you're perfectly right. It would be good to include those data, but then somebody comes and says, well, of course, the cultural attitude has been omitted, and now you have it, but there are more variables which are omitted. And you must include all omitted variables to get valid regression. So it is the best way to get the data, I agree, but sometimes that's either difficult or it doesn't really help because you can always be criticized as having omitted some kind of variables. Right, so the solution here that we are going to talk about is exactly the idea that over a relatively short time period, some of the variables will not vary within the state. So the cultural attitude is something which is relatively persistent and stable within a state. It does vary over the states, but not over time, at least not over a short time within a state. And this is a property that we can use. And this is called fixed effects regression. So let's simplify the problem a bit. Let's only look at two periods, before and after the comparison. So we exploit the panel data structure to get, in a way, to get rid of this omitted variable bias problem and to get rid of the criticism that some omitted variables are still there. And we only look at two periods to start with. And what we are going to do is we will focus on the change in the dependent variable and compare that to the change in the regressor. Okay? All right, and then we look at the before and after comparison of the two values. And in that way, we will quickly see that in this way, since we assume that within the state, the cultural attitude doesn't vary over time, we can actually get rid of these omitted variables. All right, so let's consider a variable that has an impact on the fatality rate and does not change over time. So this Z is not an instrument here, but some kind of omitted variable. Okay, so it has an impact on the fatality rate, and it does not change over time. The cultural attitude, for instance. If you live in a community where it's just usual to drink and then drive, that of course has an impact on the fatality rate. And it's unlikely that this attitude is going to change over a small time period. Okay? So we assume that this variable does not change at all. And therefore, there's no time index here. It's Zi, not ZIT. We have XIT and YIT and the error terms IT, but not ZIT. It's only ZI because it doesn't change over time. And then we regress, or we assume that we could regress the fatality rate on the BRTX. And that's the variable which we are interested in, or the slope coefficient of this variable we are interested in, and this additional variable Z. Okay. And we do that not only once, but twice. Okay. So we do that for 1982, and we have the fatality rate in 1982, and the BRTX in 1982, and the error term in 1982, and the cultural attitude, which doesn't vary. So there's no year index here. It's only ZI. We do the same for 1988. So that's the fatality rate in 1988, BRTX and error term. And here we have the cultural attitude in 1988. It's the same because it doesn't change over time. All right, so we have two regressions here. Now we subtract them from each other. We subtract the first from the second one. So on the left-hand side, we have the difference in the fatality rates, the increase or the change in the fatality rates. Then we have intercept minus intercept, drops out. So there's no intercept here. Then we have beta 1 times the BRTX in 1988 minus beta 1 times the BRTX in 1982. That's the term here. Then we have beta 2 Zi minus beta 2 Zi, cancels out, and the difference of the error terms. Error term 1988 minus error term 1982. So we have a new regression here. The endogenous variable is the change in the fatality rate. We don't have an intercept. And we have the exogenous variable here, or the regressor here, which is the change in the BRTX. And we have an error term, which is composed of two other error terms. But we could just use a new symbol for that. So it's just an ordinary error term. And the cultural attitudes are just gone. They just disappear. And the good thing is, it's not only cultural attitudes, it's all omitted variables that do not change over time, that disappear here. So the criticism that some omitted variables are still omitted doesn't really apply here, because all potentially omitted variables that do not change over time cancel out here. It's not just cultural attitude, it's all variables that are constant over time. And that's a lot. Yeah? So that's really a very good trick. And panel data is a very powerful approach to causal inference, because using panel data, this omitted variable bias problem vanishes, at least in so far as it concerns variables that do not change over time. And that's why it's called fixed effects. It doesn't change over time. Any questions so far? So the idea here is really to look at changes, and then everything which does not change drops out, because the change in the cultural attitudes is zero. Yeah? The beer tax changes, and the fatality rate also changes, but everything which does not change over time will just drop out.
Is there a possibility to come back from these changes that we are looking at now to the absolute values? Because couldn't it be a problem if we only know how a change in beer tax affects fatality instead of knowing what would be the optimal beer tax? Because it's always depending on what the beer tax was before. If I had like no beer tax at all, then it might be a different effect of a change in the beer tax than if I have already a really high beer tax.
That's correct, yes. In a way, we can come back, but at this point, we actually can't. Yeah. So here we only know the value of the coefficient beta 1 if we do this estimation. But that's the value we are really interested in. Yeah? So that's the causal effect. So we succeed in really estimating the causal effect, but you're right. If we want to say more about the impact of the level of the beer tax on the fatality rate, this doesn't help. Yeah, we come back to that. Yeah, maybe today. Okay, so let's briefly repeat that. ZI, for instance, the cultural attitudes, doesn't change over time. So all the changes in the traffic fatality rate must have other sources. And potential sources are change in the beer tax, of course, or changes in the error term. And the error term captures everything that, well, changes over time and is different in different states. Okay, so the important point here is that if we look at the changes, then we're actually controlling for all the variables that do not change over time, because the change in those variables is zero and they just disappear. Okay, so that's a very powerful method, because the usual criticism that there are omitted variables doesn't apply here. And this is the outcome. So if we actually run that regression, we have a negative slope. So the change in the beer tax is down here, and the change in the fatality rate is here. And we can see that the slope is negative. The higher the beer tax, the more we increase the beer tax, the more the traffic fatality rate decreases. So if we decrease the tax rate, then the fatality rate will increase. Not saying anything about the level, only the changes. Okay, that's the same again as a formula. So the change in the fatality rate. We have included an intercept here. We needn't actually do that, but since most software packages just by default include the intercept, it's still here. And then that's the term we're interested in. And it's negative. And it's also significant. Can you see that? So you can immediately see that it's significant because you use about twice the error term. Oh no, the t-test is the estimated value minus the hypothetical value. So -1 minus 0 is -1 divided by the standard error. The standard error is 0.3. So 1 divided by 0.3 is 3, roughly. And that's larger than 1.96. So it's significant. Yeah.
Isn't it a problem that the intercept is not significant?
No, because theoretically the intercept is exactly 0. Actually, let's go back to the previous, this one here. So if we look at the differences, then the intercept cancels, because the intercept is also time invariant. It doesn't change over time, it doesn't vary over time. So there's no intercept here. And if we really closely stick to this regression equation here, we should estimate that without an intercept.
But how can we be sure that the intercept doesn't differ over time?
That's an assumption. We come back to that. So we are going to look at models where the intercept does change from year to year. Yeah, but at the moment we assume that it's constant. We also assume, by the way, that the causal effect of the beer tax is the same in all states. So how do we know that the impact of the beer tax on the fatality rate is the same in Alabama as in Wyoming? That's an assumption here. So we could say that the beta 1 might be different in all the states. Could be. Yeah. Actually, you will be equipped with methods to deal with these cases, but we won't do that in this course. But using the methods that you have already learned, you might deal with that. So the intercept here needn't actually be included, and the fact that it's not significant is actually reassuring. So it's good that it's not significant, because our theory, our assumptions say that it should be 0. And even though we know that it should be 0 by assumption, we have estimated the intercept here because it's just by default done by the computer, and that's no extra effort, but it's quite reassuring that it's not significant. So this is not a problem. It's actually a good result. Okay, so, well, the authors give an interpretation of the negative intercept here, but I don't think that's really convincing, because this is not at all significant. So I think we better skip that. The slope coefficient is significant. So we do find evidence that increasing the beer tax is good for lowering the fatality rate. And actually, it also gives us the amount of death which are saved here. Okay, so that's the main idea of what's called the fixed effects canal regression. The main idea is to keep fixed the potentially omitted variables, then look at the differences, and in this way, to let all the omitted variables which do not change over time, we call them time invariant, to disappear. Yeah? That's the idea. And it's called fixed effect regression. And it's a method for controlling for omitted variables that do not change over time. Right, we've seen this before. Well, that's exactly the same regression equation again, but for more than 2 periods now. So we not only look at 2 periods, in this case here, we look at any number of periods and any number of individuals. And what we would like to know is the value of beta 1, because this will have an impact on our policy decisions, and we should have a consistent estimate, consistent estimator for this causal effect. All right, so let's go back again. We can see here that this term does not change over time, just as before. So that's also true if we look at more than 2 periods, of course. And therefore, if we merge the intercept and this time invariant term, we could call that alpha I. Go back again. So we merge the intercept and this term here. And we call that alpha I. And then we can rewrite the equation in this way. And we can see here that essentially using these time invariant regressors means nothing else than the intercept is different in each state. Okay, so we have different intercepts in each state. And that answers your question in a way. So we have a different level in each state, but the slope coefficient is by assumption identical in all states. We were interested in the slope coefficient. We have the slope coefficient, so then we can use the slope coefficient and adjust the intercept state-wise. Yeah? So in this way, it answers your question, I think. All right, so if we only look at one state, then we have a population regression line for that state, which looks like this. And we can see here that the slope coefficient, by assumption, is identical in all states. If you don't believe that this assumption is a good assumption, then of course you shouldn't make this assumption. But quite often it's reasonable to actually assume that the slope coefficient is identical in all entities. Okay, and everything that is really attached to the state has been merged into this individual, into this state effect, into this fixed effect here. So let's think about a different application. Let's assume that you're interested in the level of earnings of individuals. So let's say YIT is the earnings of individual I in period T. And you would like to explain the earnings by, for instance, the education. So XT would be the number of years of education. Then of course the education has an impact on the earnings. The better educated you are, the more you're going to earn on average. Not everybody, of course, but on average, that's the case. But of course, there are other impacts on earnings, which occupation you're going to have, how clever you are, how diligent you are, and so on, how much effort you put in. So there are many, well, character traits that have an impact on the earnings, apart from education. Gender might also be a factor. If you have discrimination on the labor market, then gender is also an effect which might have an impact on earnings. Now, if you try to run such a regression where YIT is earnings of individual I in period T, and this is education of individual I in period T, then all the character traits that have an impact will be merged into this intercept term for individual I. Okay, so everything that doesn't change over time, how clever you are, what else? Well, your gender. It doesn't change over time. And everything that doesn't change over time is just merged into this individual fixed effect. And the problem then is that you can't find out the impact of those time invariant variables. So if you're interested in the discriminatory, whether there's discrimination in the labor market or not, you might be interested in the effect of being male or female. That's one exogenous variable which is relevant here, but it's time invariant. So if you look at changes, this variable just drops out, and you can't use the regression to find out the impact of time invariant variables. Strange term, but it's correct. So such a fixed effects regression would not work for estimating discrimination. All right, so how can we estimate the model? Well, we have the different intercepts and we call those the fixed effects. Sometimes they're called the entity fixed effects or individual fixed effects, but we just call them the fixed effects. And then the variation in those fixed effects comes from omitted variables that do not change over time, like cultural attitudes, like gender, like whatever. We can rewrite the model. It's pretty easy actually, by introducing dummy variables for each individual. Save the first one. So we introduce the dummy variable for individual number 2, which takes on the value 1 if the index I is equal to 2 and 0 in all other situations. Then 3, 4, 5, and so on. And the dummy variable for the last individual takes on the value 1 if I is equal to n and 0 in all other situations. And if we do that, we can rewrite the model with these dummy variables in this way. So we have an intercept again. We have beta 1 times the regressor. That's what we are interested in. And then all the dummy variables. From second one to the last one. Those are just ordinary regressors. Yeah. So dummy variables are regressors like any other regressors. There's no problem in using dummy variables.
What is the difference of dummy variables with beta 2 and Z 10?
Zi is the value for some variable for individual I, for instance, cultural attitudes. Di only takes on the value 1 or 0. So Zi could also be 5 or something, but the dummy variable is always 0 or 1. And if you look at the Zi variable, then it really just drops out of the regression if you go over to the changes. But this regression here could be estimated using all the observations. So in this way, we would also answer your question. So here again, we would get an estimator for the intercept and the beta 1. That's the same as before, but we would also get estimates for the intercept which belongs to the individual I. So here we would, in a way, get estimates for the alphas, for the different alphas. So the first alpha, the intercept for the first individual, would be just the intercept beta 0. The alpha for the second individual would be beta 0 plus gamma 2, because for the second individual, this one is 1 and everything else is 0. Okay, so the intercept for the second individual is beta 1 plus gamma 2 and so on. So this dummy regression would actually work and would give you estimates for all the individual slope intercepts. All right. Clock is working again, so we have 4 minutes to go. And that's not much. Are there any questions? Okay, so the plan for next week is to do the rest of panel data regression. It's not that much. Then the week after is there's no lecture on the 12th, because that's the week where you do the home assignment. And then there could be one last session on the 19th. So if you're interested in, say, question time on the 19th, we could have a last session in the last week, but that need not be the case. So we can see that later on. But the plan for next week is to do the rest of what we're going to deal with in this course, the rest of panel data, and then we are through. Okay? So then I hope you are well equipped for doing empirical work on your own. All right, so let's stop here and see you again next week. Bye-bye.